be talking about performance characterization of MPI libraries on ARM-based AWS HPC cloud instances with elastic fiber adapters. So this work is done at our lab at Ohio State University, and I'm presenting on behalf of the group. Next slide, please. So this is the outline of the slide. So I will initially talk about, introduce the problem, the elastic fabric adapters, and recently the emergence of ARM-based CPU systems. And after that, we'll talk about some of the MPI optimizations that we have done. And after that, we will do some performance evaluation, and this evaluation will include micro benchmark level performance and also application level performance. And towards the end, I will conclude. Next slide, please. So Elastic Amazon EFA adapters are enhanced versions of Elastic Network adapters. These allow operating system bypass. The bandwidth is up to 100 gigabits per second. These adapters support network-aware multipath routing, so which means that if there is some kind of issue on one of the available paths, the networking technology is capable of choosing other alternate paths and without overall impacting the performance. In terms of programming or exploiting this networking infrastructure from MPI communication runtimes, it is possible to do so using a couple of interfaces. The first one is IB verbs, and the second one is libfabrics. Most of the MPI libraries out there today, they utilize libfabrics, and in this work we will show that in MUpage2X software we are actually utilizing the support for EFA through IB verbs. EFA introduces a new Q-pair type, which is called Scalable Reliable Datagram, SRD in short. So this is similar to Unreliable Datagrams, UD, and currently there is no support for RCs on these particular systems. And in terms of the evolution of networking on AWS, these ARM-based HPC instances became available in 2021. These are called C6GN instances, and these are also equipped with ARM processor, but these also have EFA adapters. So essentially, in this talk, we'll be doing some characterization on ARM-based systems, those that are equipped with EFA adapters. Next slide, please. So when we compare SRD with existing protocols like UD, some of the main differences lie in reliable delivery. So UD does not support reliable delivery, but SRD guarantees delivery of packets at the receiver end. Because it's a reliable protocol, the global routing header is not required, which is required in the case of UD. And in terms of the MTU size compared to UD is also doubled. So it's basically gone up from 4 kilobytes to 8 kilobytes. So when another feature of SRD, this provides out of order. The networking fabric or the underlying technologies are providing out of order delivery. It means that the MPI library has to do this extra part of providing, putting the packets back in order and providing these back to the HPC applications that are using them. So this is a little bit of extra work for MPI libraries. And in terms of providing multiple ECMP paths, there are no hotspots, and it's possible to have fast and transparent recovery from networking failures. And the congestion control algorithm for SRD is also designed for large scale, and which results in minimal jitter and tail latency, which is useful for HPC based applications. Next slide, please. So if you're doing HPC on AWS instances, there are a variety of hardware available. So you can choose from x86, Intel, AMD processors, and more recently also ARM-based CPU types. And obviously, just like any other cloud system or platform, it's possible to run instances with different hardware configurations where there is different virtual CPUs count and storage and networking bandwidth. So the recently supported ARM-based instances, these are custom built by AWS, and these use 64-bit ARM Neoverse cores. And these, we have seen that these provide pretty good performance for workloads running on the Amazon EC2 cloud. And again, as I mentioned, the networking bandwidth available is 100 gigabits per second. And with AWS parallel cluster, it's possible to quickly deploy HPC environments. It supports multiple instance type and also multiple job schedulers. Um, there is also support for different operating systems like Amazon Linux 2, CentOS, Ubuntu, and there is flexible, cost-effective allocation, which means that the users can launch whenever um, the the infrastructure is required. Next slide, please. So let's now talk about supporting MPI libraries on AWS EC2 HPC instances. So basically, when we talk about running HPC applications, so they would have to use some kind, if the application is scaling out, they would have to use some kind of a communication runtime like OpenMPI or Intel MPI or MPI2X. So as I've briefly covered before, if these MPI communication runtimes would like to exploit EFA adapters, they can do so. They have two options: either use libfabrics API or use IB verbs and utilize the SRD protocol. So in the case of OpenMPI and in Intel MP, these are relying on libfabrics as is shown on the right-hand side of the figure. So with libfabrics, it's possible that it can bypass the underlying Linux kernel driver and talk directly to the EFA device, which is obviously going to be very efficient. In terms of MPI2X, the AWS version, we work on top of SRD verbs. And SRD verbs is essentially also makes use of the EFA kernel driver, and at times it also is capable of talking directly to the underlying EFA devices. So the details of the architecture that has been adopted in the MPI2X library is detailed in this particular paper published in HOTA in 2019. And essentially in this paper, what we talk about is if the networking fabric is providing guarantees for, it's providing a reliable transmission of the packets, but the packets are out of order. So in this case, what happens is the MPI library has to put these packets back into some kind of order and return to the calling application. So the protocol that we have used and why existing protocols do not suffice are detailed in this particular paper. Next slide, please. So with this, now I will talk about some of the optimizations that we have done in the MPI2X library. Next slide, please. So the MPI2 software, I think, as was covered in the earlier three talks, is an high-performance open-source MPI library. It supports multiple interconnects: InfiniBand, UniPath, Ethernet, Rocky, now EFA as well. And recently, we also added support for Rockport and Slingshot. It works on multiple platforms. The project has been around for 21 years, and it is powering some of the top 500 clusters out there as well. It's been used by more than 3,000 organizations in 89 countries, and the software, the direct downloads from our websites have been around 1.57 million downloads. Next slide, please. So in terms of MPI optimization, so there are basically two main optimizations that we have done when it comes to running MPI2X on the AWS platform. Whenever we are porting MPI2 library on a new platform, obviously each platform has its own characteristics. So for that reason, it is needed to do collective algorithm tuning. So, for different message ranges, which algorithms are going to perform for on different architectures. So this basically entails, iterating through different collective algorithms, in combination with a number of nodes and ppn, and determine which particular algorithm is providing best performance in different scenarios. So obviously, when we ported MPIGE2 on AWS platform, so this was one thing that we had to do, and this essentially results in choosing the most, in terms of optimal, in terms of performance, the most optimal collective communication algorithm on the available platform. And the second optimization that we have done is utilizing the XPMEM kernel module. So XPMEM is essentially a kernel that optimizes shared memory communication, and it's really useful for communication of small messages on, large messages on intra-node communication. So if you're only utilizing, let's say, a single processor and you have multiple processes running on them and they're communicating to one another, so XPMEM module performs much better than the existing alternatives that are available there. And MPIGE2X is, can automatically detect the installation of XPMEM module, and it can, load that and try and utilize that. So now, when we are running collective algorithms, or whenever, let's say, we are running large scale applications, so if there is any communication going on intranode communication going on between processes on the same node, so now it is possible, because of this module, it is now possible to utilize this efficient module compared to the previous existing the options that we have. And the benefits of the collective communication algorithms are shown on the right hand side. So here we are showing two graphs. The top one here is the scatter graph, and basically we are showing this for 16 nodes. And here we are utilizing, this is basically full subscription, which means each node has 64 ARM cores, and we are running 64 MPI processes on the node. And on the top, you can see for scatter, we are plotting for the messages from 4 bytes until 512 bytes, and we can see the red graph here is the default MPIGE2X software, and the green one is essentially the optimized one. And the bottom graph here is essentially all reduce. Again, 16 nodes, 64 ppn, and again, as we see for large messages, we see that because of the optimizations that we have done, these are actually providing us some better performance. Next slide, please. So now I will talk about some more performance characterization. I'll talk about the experimental setup and then talk about the micro level performance and application level performance. Next slide, please. So the experiments that we have done are on the C6GN 16x large instances. The RAM here is 128 gigabytes. The libfabric version is 1.13.2, and parallel cluster version is 3.0.2. And OpenMPI that we have used is in essentially 4.1.0, and MPIGE2 software is the latest MPIGE2X AWS version. And the OSU micro benchmarks that we are using are version 5.8. Next slide, please. So in this figure, we are plotting point-to-point evaluation. And here, basically, we have three plots. The leftmost is the small latency plots, and then the large message latency plots. And then on the right-hand side, we have the large message bandwidth plots. And as you can see, we are basically comparing MPIGE2X AWS, which is the red worm here, with the green worm, which is OpenMPI. And in terms of latency for small messages and large messages, the performance of MPIGE2X AWS is similar to OpenMPI. However, for the large message bandwidth, the red worm is lagging behind OpenMP. So again, OpenMPI here is utilizing the libfabrics interface, and MFH2X AWS here is utilizing the SRD path to EFA essentially. But we do see that OpenMPI is performing better for large message bandwidth in this case. Next slide, please. So here we are essentially showing results for single node collective performance. So because this is single node, so the optimization that I just discussed about XPMEM is going to be very relevant here. So we are plotting numbers for 4 collective algorithms here, starting with all gather on the top left, and then top right is all reduce, bottom left is gather, and bottom right is essentially scatter. So for all of these algorithms, we are only utilizing a single node, as I mentioned, and this we are also running all the 64 cores provided by the ARM processor. So we see that for all gather, all reduce, and just the gather operation, we are seeing gains for the small message range, close to until 1 kilobytes we are seeing gains, and for at certain points these are up to 5x and 6x gains. However, for scatter operations, the gains are only for the large messages. So as you can see, we have around 5x gains for large messages when we compare the performance of scatter. So again, so XPMEM is going to be relevant for large messages. So here, the gains coming from XPMEM, and XPMEM is only contributing. It's not the primary, factor between the gains between MFH2X and OpenMPI. So essentially, but mainly, the collective tuning, or the different algorithms utilized would be playing a factor here. So the next slide. So here we are providing cross architecture comparison. So we are basically running MFH2X software on ARM instances compared to Intel instances. So again, these are these numbers are going to vary because this is a different architecture. There will be different allocations, and we actually see that as well. On the left hand side, if we see small message latency, we see that the ARM systems are depicting lesser or faster latency. And if we look at the right hand side, again, the ARM systems are delivering better bandwidth compared to the Intel systems available. But again, as I said, these are different resources running at different time zones. So because of that reason, there can be some performance discrepancies. Next slide, please. So here we are basically plotting 4 nodes collective performance. So we are plotting all gather, all reduce, gather, and scatter, again for 4 collective algorithms. And as you can see here, we basically again have competitive performance against OpenMPI. And again, the results shown here are again 64 ppm, so utilizing all the ARM cores available. Next slide, please. So these are some larger scale results. So here we are utilizing 32 nodes and fully subscribed 64 ppm. And we again witness similar performance gains here around. Again, the performance varies for different algorithms for different message range, and as we have circled here, the gains are more pronounced for some message types. So for example, for 6x in all gather, 5x for all reduce, 5x for small messages in gather, and 3.2x on scatter. Next slide, please. So we also did some application level performance comparisons, and in this case we went with this WRF, which is a weather modeling and forecasting application. So on the left hand side we have this weather forecasting applications. It's called WRF for short, and these are essentially strong scaling results, and the input data set is the 12-kilometer resolution case over the continental US domain. So here we can see that, again, this is full subscription. So 2 nodes, 8 nodes, 16 nodes, and 32 nodes. And we can see here that with 32 nodes, if we compare the performance of MPI2 optimized with OpenMPI, we are actually gaining around 30% of the performance, so which is a substantial gain for application developers. On the second application that we have here is the mini adaptive mesh refinement application. And in this case, again, we are running three MPI libraries: MPI2X default, MPI2X optimized, and OpenMPI. And for again 2, 4, 8, 16, and 32 nodes, all fully subscribed, 64 ppn, and we see around 30 on 32 nodes, we see around 19% gains from the OpenMPI. So next slide, please. So all of this results are actually published in our recent paper, this AP DCM workshop at IPDPS. This paper is mainly essentially the source of many of the plots in this particular graph, in this presentation. Next slide, please. So with this, I will now conclude the talk and discuss the future plans. So ARM-based cloud systems are actually, they have emerged, and these are providing a competitive option for HPC application users. And these are actually quite useful for compute-intensive workloads as well. The performance optimizations of MPI libraries, or any other communication runtime, obviously we would like to make the maximum out of the hardware available to us. So just like x86 platforms, optimizing on these ARM-based instances also lead to better performance. And in the future, we plan to do further performance optimizations on the upcoming Graviton Generation 3 system on AWS. And we are also engaged with other cloud providers like Azure, like Oracle, to optimize the MPI2 library on their platforms. We'll continue to further partner with AWS and continue optimization on these ARM-based GPU systems on AWS or other cloud systems. So next slide, please. I think with this, I would like to thank all of you for listening. I apologize for the issue. I had actually added some material in my local copy, but I couldn't present that. But I guess that's fine. So thanks a lot for your patience.
So we had a couple of questions. Benson asked if there's a way to quantify variance in performance, as it might be useful for quality of service guarantees.
Right. So when we are running OMB benchmark, so OMB benchmark would cater for variances up to some extent. So the numbers reported here are, so there is obviously a warm-up stage. So we, ignore the initial warm-ups, and after that, the OMB, software or the micro benchmark will, take care of the variance. And the numbers we are reporting here are actually the average of several runs.
Okay. Jim is asking for the reason, what the reason is for the large bandwidth difference between ARM and x86.
That's right. So again, so Jim, when I presented those numbers between ARM and x86, these were two completely different instances. Maybe the data center was also different. So, I mean, the expectation here matches what has been, published by Amazon. Amazon, when ARM-based instances came out, it was advertised that there is 40% better, packet processing. So essentially, that's what we see as well. Maybe Brian here would like to add something there. Yeah, Brian might be mute.
Yeah, the big answer there is just that C6GN was the first platform with our second generation of EFA hardware, and the bandwidth curves are the peak bandwidth ends up being the same, but how fast we can ramp to that is much better in the second generation because it's newer, so it's better, right?
And not so much a question, but this was discussed in the chat as well. How much? Two questions actually. So what is your take on XPMM being more widely available, but Jim chimed in and said OpenUCX is maintaining it. The second question is, have you had a chance to look at CMA, and given that upstream, how does CMA compare with XPMM on this, like an ARM-based platform?
So we have not done comparisons with CMA on ARM-based platforms, but we have done on other Intel-based systems. On Intel-based systems for large messages, XPMM was giving better performance, but we have not done this evaluation on ARM-based systems.
Okay, are there any other questions or comments on this great talk? Okay, well, thank you very much, Amir. Appreciate it.
Thanks, everyone.